Let's begin section 11.2, recalling 11.1 being limits. And we did all kinds of things with limits. We knew it was a limit if f of x, as x approaches some constant, equals the value, some value from the left, and that if the function existed approaching some a to b approaching from the right the same, then the limit existed. And this was even if f of a equals undefined. In other words, there is no solution. So we had that to contend with. Well, now we're talking about continuity. Well, what the heck is continuity? Continuity is when you can use a writing instrument when using a pencil, on a graph, does not jump when a gap occurs following the graph. Okay, well, what else can we say about this? And my pen is struggling. There's something wrong with my pen. Let me take another pen. Okay, well, what else can we say? Therefore, we can state a graph is continuous if the limit for each x value the domain. It's continuous. So I can have this graph. It is a specific domain, but there is no graph. So I can follow this as it goes. Well, what if I had this graph? What if I had this one? Well, at this value, the line is discontinuous. Therefore, not function. Sorry about that. Well, we have another condition here. Supposing I have this line. Well, in this line, we have all the conditions for x till we get here at a removable point. One is not continuous. So now let's study this material. Let's study it. All right, here we go. Continuity at x equals some value given in the function. A function is continuous at x equals c if the following three conditions are satisfied. To be continuous at the point of a specification, three things have to be. F of c is defined. This means f of that c is a real number. Can be negative, can be positive, can be all kinds of things, fractions, whatever, but it is a number. And then we look at the limit exists. For and after that point. And then this one, if the limit as x approaches c of the f of x is the outcome of it, then all three conditions are met. Okay, no gaps. Right, so let's do some discontinuity references. And this applies to rational functions. And in this book, they refer to it as look at my notes here, make sure. X and Q of X. So then we would factor the denominator and find all values ahead of myself of X that create a zero in denominator. Or a removable point. Because it doesn't fit into that item. Then we also have radicals. So in a radical, we have a restricted domain. So we have to verify it's not at the start or end of the domain. Now, you know, if it's at the start, we would have some x value to infinity. And if it's at the back end, because x is negative, then we would have, in this case, negative infinity to an x value. So if a limit does not exist if we have one or the other. All right. So let's look at an open interval and a closed interval, because that's what we were discussing above. A function is continuous on an open interval if it's continuous at every x value in the interval, not at the endpoint, in the interval. A function is continuous on a closed interval, AB, if it is continuous at an open interval. That means it's in between the endpoints. It is continuous from the right at x equals a, and it's continuous from the left as x equals b. So that means there has to be positions around it in order for it cannot be the endpoints. All right, so let's look the interval over which the function is continuous. So our first step is to find the domain. So we have 7x minus 9 has to be greater than or equal to 0. 7x is greater than or equal to a 9. We're going to divide by 7. So our domain is 9/7 to infinity. Now, we have to determine the interval for which the function is continuous. It defines function continuous. No brace. All values in that are good. All right, that will be the interval. Now we have this condition here that we want to discuss. Find all values of x equals a where the function is discontinuous. For each of the points of discontinue, give the limit as x approaches f. All right, from the negative and the positive, and then state if it exists. All right, so first we're going to find points of discontinuity. All right, so our first point is this guy right here. Yeah, and it is 1, 2, 3, 4, 5. -5 is the point of discontinuity. All right, it is a function. For every value, there is that consideration. So now, the second part says, find the limit as x approaches -5 of f of x. Right. So as I approach from the left, I get f of x equals, and that's a -1, 2, 3. It's a -3. All right. So now I have that. That's the A part. And it is, and also we know that the limit as we approach it, well, the value of f of -5 is -3. We also know that because it's a solid point. Now our C says find the limit as it approaches from the right. Oh, this was from the left. So as I approach it from the right, it approaches the positive value of 1, 2, 3, 4, 5, 6, 7. Seven. All right. So you can see between these two, don't have a removable point, but we have a gap. So this gap means that we can safely say now that on the D part, on f of -5, that value, -3, that's what it wanted, and identity of f approaches identity x identity is continuous on us. We can safely say does not exist. There is a gap. So that is what continuity identifies. You go from the left to the right, see if f of x exists, and go from there. So here we have a rational function. Right. So we want the values of a, where the function is discontinuous. Or, excuse me. For each value, give the limit of the function as it approaches a. Be sure to note when the limit does not exist. All right. So our first step is to set denominator to 0 and solve. Right. So here we go. X minus 2 cannot equal 0. So we want to make sure these are where the holes are. So let's get started. That means, try again here. Well, it won't let me here. So we're going to say x equals 0, so it does not exist there. And x plus 2 equals 0, so x cannot equal -2. So values of x equals 0 and x equal -2 are vertical asymptotes, or a removable point. In this case, they're not a removable point. They're asymptotes. All right. So we figured out first where it is discontinuous. All right, so we have no values. Now what they want us to do is to give the limit as it approaches these guys. All right, so we need it from the left. And so we could do f of negative 0.001. All right, it's pretty close. Find out where it's going. And then we would do the limit as x approaches 0 from the right as f of positive 0.001. Not too bad. All right, so let's look at this guy. Here, whatever I was working on. Now we're going to enter a rational expression. Remember, we're going to enter first our parenthesis, the numerator, 1 plus x, parenthesis, divide symbol, and then enclose the denominator as well. So we're going to have x, parenthesis again, x minus 2, close parenthesis for that rational, and close parenthesis for the denominator. And we're going to go, let's do zoom 6. All right. And you can see we have exactly what we thought we had. They're asymptotes. And so we want to do second calc value at negative 0.001. We get a large number, right? Because as we're approaching the negative, it's going to infinity. So let me move this guy over here. So we're going to get, sorry about that. We're going to get approximately 499. Yeah, you know. Okay. At, from the right, 0.001. Okay. We get a negative 501. All right. So, gap. Want us to find the limit. And the limit as x approaches 0 of f of x does not exist. All right. So we did that number. Now we're going to do other number, which was negative 2. Positive 2? Let me look. What did I enter? Let's see. Negative 2. Oh, I did a mistake. Sorry about that. It's a positive 2. But he caught me. Okay, here we go. And I'm going, what? So now we want the limit as x approaches 2 from the left of f, and we're going to put that number as it approaches 2 from the left. We're going to make it 1.999. All right, so we're going to do a second calc value, 1.999. Very close to 2, isn't it? And it's a negative 1,500. Then we're going to do the limit as x approaches 2 from the right. So it's a little bit larger than 2, 2.001. All right. Second calc value, 2.001. And this time we get a positive 1,500. So gap. So the limit as x approaches 2 of f of x not exist. All right. So we've done that part, and we've answered all of the questions. Now this one's important only because it has an absolute value numerator. that it's a v, and it's divided by the x plus 1, which looks like 1. In other words, does this cancel that? Well, of course not. Of course not. But we're going to probably get a 1 for it. And this one is probably going to be a removable point. So it says, find x equals a where the function is discontinuous. All right, so we're going to set the denominator equal to 0 to find a. So x equals -7. All right, but we know that the numerator has x plus 7. So whether it's a negative or a positive, it's going to be approaching 1, as you can tell, because they're the same. But we're going to find that out. All right, so now they're asking us, does a limit exist as it approaches a? All right, now it's not asking continuity. It asks, does an x have a value? All right, so we want to test for a limit. So we want, limit as x approaches -7 from the negative for f of, okay, we're approaching from the left, so we're talking -6, would help if I put the negative, right? -6.999. All right, we're going to use a calculator, of course. Limit as x approaches -7 from the right. So that means a little bit larger than that 7. Ooh, do I have it backwards? Oh, this is the larger. Sorry about that. Bad math here. This is from the positive and this is from the negative. Sorry. I don't want to rewrite the whole thing. Negative numbers is a reverse, isn't it? So this is smaller side, 7.001. All right. So let's put it in our calculator. Now you can do second math and do absolute value, but I like second catalog, and it's the first one. Now mine is a 84 plus CE, so it's got the little bars. Yours are going to have parentheses, and that's okay. So I'm going to put in what I have, x plus 7. All right, and I'm going to get out of that, and I'm going to divide by parenthesis x plus 7, close parentheses. I'm going to go zoom 6, and that's what I have. And one of them is on the negative side, and one of them is on the positive side, but they're both reaching 1. But because they're coming from both ends, I'm going to do a second calc value, and I'm going to enter -6.999, and I'm going to get a 1. So close it is. Then I'm going to enter the -7.001, and I get a -1. So, does it exist? No, there's a gap. Does not exist. And that's where the absolute value affects what is going on with the problem. I was positive on the top side and negative to the left. Very good. So here we go to an interesting one, and it's E. E has some properties in it that exist, and, but limited by the exponential radical. So what we have here is the radical exponent that affects this function. So it's limited by that radical. So we're going to set x minus 7 has to be greater than or equal to 0. X has to be greater than or equal to 7. So our domain is 7 to infinity. So any value in between 7 and it has a limit. Uh, so parentheses 7 to infinity, because we do not include 7 as a limit. That's the starting point. And there has to be a reference to the left and to the right to have that limit exist. So if we do put a 7, we then have 3e to 0, square root of 0, which is 3. So it exists at the point, it is continuous at every point in between, and that's all we have to do. So we know it is in this realm that a limit can exist. Cannot exist at 7. Okay, good. So let's look at a piecewise. A piecewise function is a continuous function within the domain that is said to be. So we notice here that it is a horizontal line at 14 for any value less than -1. Okay, on this one, between -1 and 3 inclusive, this function applies. And then for anything other than that, on 3, it is the other. So we want to graph this guy. And we're doing it for x is less than -1. So we're going to do a -1, and we know it is 14 with a circle. And then so that would be a -2, it's still 14. All right. So we've got that condition there. And now we're going to do for -1 less than or equal to x is less than or equal to 3. So this time we're going to put in this case, we're going to put in a -1 into our function. So a -1 squared plus 5 is 6. We're going to put a 0, and if we put in a 0, and we know it's a 5. And then we're going to put in a 3. So this is 9, 14. All right, and these are closed dots. Okay, so now we're going to do the other one, x greater than 3, for that same function that it says 14. So it is an open hole at 3, but it's 14. That's an open hole. So then I'm doing 4, and it's 14. So let's try to graph this so we can understand if it is continuous or not. So we started with -1. So here we go, -1, 3. All right. And these are 2, 4, 6, 8, 10, 12, 14, 16, 18, and so forth. Okay, because I think 14 is the magic number. So we're looking at this portion right here. And we're going to do this one in blue and then change colors. All right, for this one, I have -1 and 14 as a whole. And then at -2, I have a 14. So we have this condition. All right, and trust me, it should be a straight line and you get it. So we're going to do, for this one, we're going to use green. At -1, at a 0, it is 5. And at 3, it is 14. That's interesting, isn't it? -1, it's 6. At 0, it is 5. At 3 is 9 is 14. Yep. Oh, it's a parabola. At 3. Sorry about that, class. So what did I do? And it is a solid dot. So we're going like this. The dot. Okay, continuous through the whole thing. Now we're going to do our last one. For greater than 3 is in red. 3, 14 with a hole. And then it is 14 for the rest. And I drew that kind of crazy. Try that again. It looks terrible if you print my notes. Well, then it's going to look really bad. All right. So now there you have it. All right. So it says B, find all values of x where the function is discontinuous. Discontinuous would be this one. It's discontinuous. All right. And then C says, see where the function is, find the limit from the left and the right of any value of the function is discontinuous. All right. So we're going to find the limit. Minus and plus. So here we go. We want the limit as x approaches, and we know it's -1 from the left. So this is a g function. G of negative, the left, it's negative 1.01. All right. And then we would want the limit as x approaches -1 from the right of g of -0.99. All right, here we go. So we're going to do a little bit math. On the left, we know that G of negative 1.01 equals 14. And here we want G of 0.99, which is that problem, which is a negative, it's a negative 0.99 squared plus 5. All right, so we're going to talk about that. And I don't have that graph on there, and I'm not going to do that one. I'm going to do it on the home screen. So on that one, I'm going to have parenthesis negative 0.99. That's the number from the right. And that's this number right here coming from the right. Squared plus 5. Oops. Plus 5. And I get okay. So they are with a gap. Okay, then we have to do, according to what we're studying, we have to do f of negative 1 equals, and we said it was 6. So none of the numbers match. So the criteria is broken as to a continuous function, and a limit cannot be taken. On this other one, it can be taken. Right, so learning a lot. Sorry about that. There we go. All right, this is our last problem on this section, and it's ugly. And it says, use a graphing calculator to tell whether the rational function below is discontinuous. So let's do that. So 1 for the grapher. So we're going to go to the y equals, and y equals entry, and the entry is going to be parenthesis x squared plus 3x plus 10, and the denominator, parenthesis, close parenthesis, and this is divide, x cubed minus 1.2 x squared plus 4.16 x minus 7.68. Right. So let's go on our calculator. I'm going to clear that, go y equals, we're going to clear that, and we're going to enter parenthesis x squared plus the 3x plus 10, close parenthesis, divided by open parenthesis, x up caret 3, then side arrow to bring it down, minus 1.2 x squared plus 4.16 x minus 7.68, close parenthesis. All right, I'm making sure 16, okay, it looks pretty good to me. All right, I'm going to go zoom 6. Hold. So I went to the standard window and I see there is. So this says, tell where the rational function below is discontinuous. Yes, it is discontinuous. All right, verify the answer for part E. Okay, and now we need to find the value of x. So let's look at that. So we want to change our window, and I'm going to do -5 and 5, because I'm guessing it's like at 2 or something, right? Okay, here is 2. So it might be, I think 2 exists. So it might be between 1 and 2. All right. So it's somewhere in between 1 and 2. And we're going to try to figure out what it is. So we're going to start at the half, because I think it's at the half. See how this is. Let's try it half. So I'm going to do a second trace value. And I'm going to do the limit as x approaches, and I said it was a half, 1.5 of this f of x. So I'm going to find out what that is. All right, so it's a -21.9. All right, more or less. So we know we're getting close, right? So let's try the limit as x approaches 1.6 of f of x. All right, so this time I'm going to put 1.6, and I have undefined. All right, so I'm going to do on the other side. Limit as x approaches 1.7. And I get a positive 21.5. So we found it by just checking out where it could possibly be. And we knew it was between 1 and 2. And then I went, well, let's start at the half. Well, the half was negative. So I knew it was going this way. And then I needed a positive to gap it through and figure out what the middle is. Well, I just happened to hit it. That doesn't always happen, but it did. So at x equals 1.6, the function is discontinuous. All right, very good. Okay, now they wanted us to verify by using to plot and determine where, okay, verify. Well, we're going to verify by dropping in that value. And I think the function was called f of x, yeah. F of 1.6 to the function. All right, now the function was 1.6 squared plus 3 times 1.6 plus 10 divided by, and we really only care about the bottom, but we'll do it. 1.6 cubed minus 1.2 times 1.6 squared plus 4.16 times that 1.6 minus 7.68. So all we really have to enter in the calculator is this must equal 0. Okay, if we put the whole thing in, it's a lot of math. So we're going to put the denominator. If it equals 0, then we know we have an asymptote on our home screen. 1 6/10 up caret cubed sideways minus 1.2 times 1.6 squared plus 4.16 times the 1.6 minus the 7.68. I'm going to hit enter. If I have a 0, we're good. So then it doesn't matter what the top is. Find. All righty. And that is discontinuous. Okay. So the limit did not exist. It was undefined. We did it by calculator, and we're done for the course, for this section. All right, now do your homework. Thank you so much for listening.